Welcome everybody to my presentation, Inside Service Mesh. I'm Dominic Torno. I'm a principal engineer at Cisco. And as Ed mentioned, I focus on systems thinking, on systems modeling, and specifically conceptual and formal modeling to aid the design and the documentation of complex software systems. Network Service Mesh is a cloud-native computing foundation sandbox project in the category cloud-native networking. And the obligatory where is Waldo question. Waldo is actually right in the center of the map. And in this talk, we will hunt for a clear and tangible mental model of Network Service Mesh. What is a model? A mental model is a collection of facts. A collection so that every fact about the model is also a fact about the system. Mental models are the foundation of human reasoning. However, keep in mind that no model is or ever will be the system itself. Therefore, any model fails to represent the system fully. Today, we will develop three independent yet related models. First, a mental model of networking. Second, a mental model of services. And third, a mental model of network services in the context of Network Service Mesh. What is a network? A distributed system is a set of interacting components. From here on out, since we are network-centric, we call these components endpoints. Endpoints interact by exchanging messages indirectly via a network. Without loss of generality, let's focus this discussion on two endpoints, E1 and E2. An endpoint is connected to the network via an outbox and an inbox for sending and receiving messages. Also, we keep track of the sequence of send events and receive events in an endpoint's history. If an endpoint wants to send a message, it will place that message in its outbox. And placing a message in its outbox is represented by a send event. The network picks up the message from the sending endpoint's outbox and determines the receiving endpoint's inbox. The network places a message in the receiving endpoint's inbox, and placing a message in its inbox is represented by a receive event. This can also be represented graphically as a time-space diagram. Each timeline represents an endpoint's history. Empty circles represent send events, and filled circles represent receive events. If necessary, we may also represent the network in this exchange. A request-response pair, from here on out called a transaction, is represented as two messages, the request and the response, and four events: the send request event, the receive request event, the send response event, and the receive response event. And again, if necessary, we may also represent the network in the message exchange. So from here on out, we will graphically represent an endpoint's inbox and outbox as one channel, only to keep diagrams concise. Okay, so far so good. We developed a model of a distributed system. Let us explore this model a bit further. In this model, we are able to take the viewpoint of the all-knowing observer. we can observe both the inbox and outbox of E1, as well as the inbox and outbox of E2 at the same time. E1 or E2 cannot. E1 can only observe its own inbox and its own outbox. It cannot reach beyond. So from the point of view of E1, the world is simple. Messages disappear from its outbox and messages appear in its inbox. The same for E2. E2 can only observe its own inbox and its own outbox. Again, it cannot reach beyond. So from the point of view of E2, the world is simple once again. Messages appear from its outbox and messages appear in its inbox. This is a fundamental realization. From the point of view of the all-knowing observer, E1 interacts with E2. For example, E1 may send a request to E2, and in return, E2 may send a response to E1. From the point of view of E1, it places a request in its outbox, and eventually a response appears in its inbox. Similarly, from the point of E2, a request appears in its inbox, and eventually it will place a response in its outbox. It is this very realization that lets us define the concept of a service. So what is a service? Not what is a network service. We're not there just yet. What is a service? Services are definitely everywhere. There is not a single blog post, talk, or presentation that does not mention services, or worse, microservices. However, rarely do the posts, talks, or presentations attempt to define services. In order to fully grasp the concept of a service, we need to discuss different points of view. The service-to-service point of view, the process-to-process point of view, the behavioral view, and the structural view. Here we will discuss these points of view using a simple example of a service consumer and a service provider. The service provider is a key value store. A service consumer may set the value for a key via a put command and get the value of a key via a get command. Here, keys are only integers and values are only strings. Now, from a behavioral point of view, a service is nothing but a contract. A contract on the sequence of events on a consumer's inbox and outbox. The central element is the contract of the key value store. If the client places a put command in its outbox, it will receive an OK, a confirmation in its inbox. And if the client places a get key command in its outbox, it will receive a value in its inbox. Now, from a service-to-service structural point of view, in our example, we have a service consumer and we want two key value stores, creatively named key value store 1 and key value store 2. Our requirements state that we must be able to store 1,000 keys in key value store 1 and 2,000 keys in key value store 2. It's an arbitrary restriction to make the example graspable. Okay, here the client sends a put 0a command to key value store 1 to set the key 0 to value a, and subsequently sets a put 1b command to key value store 1 to set the key 1 to value b. Then, when the client sends a get 0 command, it will receive a, And when the client sends a get1 command, it will receive B. The same is true if the client sends this sequence of commands to key value store 2. The event sequences are absolutely identical. Now, how could we implement this? Here is an example. It's a simple Python Flask HTTP application that stores the key value pairs in memory. It exposes one HTTP route that accepts an integer key and responds to two HTTP methods, get and put. Get to get a value for a key, put to set a value for a key. But as we said, there is one gotcha. The process cannot store more than 1,000 keys. Remember, KVS1 must be able to store up to 1,000 keys. KVS2 must be able to store up to 2,000 keys. Therefore, KVS1 is composed of only one process, whereas KVS2 must be composed of at least two processes. For KVS1, the sequence of events on a process level is identical to the sequence of events on a service level. However, for KVS2, the world is different. Both process 1 and process 2 are able to store up to 1,000 keys. So in order to store 2,000 keys, we need to partition the key space. Here, we will store the keys 0, 2, 4, and all even keys in process 1, and 1, 3, 5, and all odd keys in process 2. Then, when the client sends a put 0a command to KVS1 to set the key 0 to value A, it has to be received at process 1. And subsequently, when the client sends a put 1b command to KVS1 to set the key 1 to value B, it has to receive at process 2. So while on a service level, the event sequence between client and KVS1 and the client and KVS2 are identical. On a process-to-process level, they are very different. However, they are indeed identical where it counts. The experience of the client, the sequence of events in its inbox and its outbox is identical. The contract is fulfilled. Furthermore, since the client is unable to look beyond its inbox and outbox, the client is indeed unable to observe the difference. The service-to-service and process-to-process structural point of view, they form a hierarchy. A service is indeed an emergent concept. Services are more than just the sum of their parts. Services are formed by a set of processes and their interactions. So intuitively, from a top-down point of view, the process-to-process level, on the process-to-process level, services exist at a set of constraints on the interaction, on the message exchange of processes. For example, for the key value store, that set of constraints determined that even keys were routed to process 1 and odd keys were routed to process 2. Now this gives us the foundation to determine what is a network service in the context of network service mesh. In the context of network service mesh, an endpoint, the provider, offers a network service. Another endpoint, the consumer, requests a network service. Then, in order to connect the consumer and the provider, network service mesh plumbs two network interfaces into the endpoints and spans a virtual via, a point-to-point L2 or L3 connection between them. Like its physical counterpart, a virtual via is a full duplex point-to-point connection. What you send is what you receive. That is, there is no frame or packet transformation on the wire itself. However, unlike its physical counterpart, a virtual via may experience message loss and message reordering. An interesting aspect of a virtual via is that of an addressing concept. Traditionally, messages carry a target address. The network determines the receiver based on that target address. If you are in a controlled environment, like for example in Kubernetes and in a Kubernetes network, you have as a developer a strong understanding of the address space. If you're in a more open environment, anything can happen. Now, the vVia gives us strong guarantees. The contract of a vVia guarantees that the receiver will always be the other end of the vVia. If network service mesh can span a vVia, it will adhere to this contract. So the network determines the receiver based on the network interface of the sender. For our key value store example, the client may request the network service key value store 1, and network service mesh will span a vVia between the client and the KVS1 process. The client may also request the network service KVS2, but KVS2 is composed of two processes to store key value pairs and one process to split between even and odd keys. Network service mesh spun a vVia between the even-odd splitter process and KVS2 processes 1 and 2. Additionally, network service mesh will span a vVia between the client and the even-odd splitter. We may rightfully say that network services are compositions. It's turtles all the way down. The vVia is a composition operator. You can have a look at the splitter. This is a simple even-odd splitter that once again exposes one HTTP route that takes an integer key. And it simply determines the modulo on this key to forward the HTTP request to another endpoint, either process 1 or process 2. And now we are able to explore the nature of network service mesh. A consumer requests a network service. For example, key value store 1. Then the network service mesh will plumb a network interface into the consumer. That is all the consumer can observe. The consumer may also request another network service, for example, key value store 2. Then the network service mesh will plumb another network interface into the consumer. And once again, this is all the consumer can observe. Now the consumer may send a put and get command to key value store 1 and receive responses via the first interface. And it may send put and get commands to key value store 2 and receive responses via the second interface. The fact that the consumer talks to a single process in case of key value store 1 and to multiple composed processes in case of key value store 2 is not only irrelevant, but in fact invisible to the consumer. Network service mesh gives us the primitives to compose complex services from simple components. That concludes the presentation. If we have some time, I'm more than happy to take questions.
So we do have a Q&A function in the Zoom webinar if folks would like to use that for questions. We also have a, in addition to the Q&A in the webinar, we also have the Network Service Mesh channel. Dominic, are you on the NSM channel on CNCF Slack so that folks can ask you questions after the talk?
I am.
Excellent. Do folks have any questions they would like to raise currently? So I think we have one in the chat from Charles Eckel. Is there any concept of virtual wires between services?
Yes, that depends a bit on your point of view. So on the process-to-process level point of view, virtual wires are spun between processes. But since processes make up services, you can argue that there is also the concept of a V-wire between a service and a service. Whereas you would say that the processes at the edge of service 1 and the process at the edge of service 2 are connected with this V-wire. However, interestingly, you can say yes, since the V-wire is also capable of composing services together once again. So as we saw in the keynote, so from simple processes you compose services, but these services can then further be composed by the processes at the edge. So yes, the V-wires can be viewed as being connections on a process-to-process level as well as a service-to-service level.
Excellent. So we have 2 more questions in the queue. And I apologize if I mispronounce your names. Nishith Tiwari asked in the chat, virtual wires, what are these, if you could elaborate?
The virtual wire is indeed just a contract. The virtual wire gives you the guarantee that if you put one message in at the one end, it will come out at the other end. just as a physical wire. So interestingly, virtual wires actually have the effect, as we already discussed, networking. In networks, you communicate indirectly via a network. Virtual wires have the interesting effect that their contract actually gives you a direct communication semantic. So network service mesh implements direct communication on an indirect message. But the point is, it is more of a contract, similar to, for example, how the Kubernetes networking model is a contract. The contract of the virtual wire states that everything that goes in one end comes out the other, and vice versa, however it is implemented.
Excellent. So we have one more question this time on the Q&A from Tom Kivlin. How possible / feasible is it to create virtual wires with traditional infrastructure, i.e. Virtual machines, bare metal based operating systems, or even underlying network infrastructure?
I would love to actually hand this question back to Ed, because I know that this is one of the reasons that makes network service mesh so powerful. It is absolutely possible, and I'm sure Ed has lots to say about that. I'm sorry if I just like throw the ball your direction, Ed.
No, that's completely fine. I mean, it's a fairly deep networking question. And probably one that's going to be really entertaining to discuss in the Panda NSM channel as well. But essentially, in terms of feasibility to create traditional infrastructure, there's a lot of feasible ways to construct it, some of which are very familiar to you. So for example, every time we create a tunnel of some sort in our physical infrastructure, whether you're doing it with VXLAN, MPLS, whatever, we end up constructing things that look like virtual wires, or we can construct things that look like virtual wires and use them to connect to things. But I think there's probably a great deal more depth in your question there, Tom. So I would suggest that we move that to the Slack channel at this time. Is that cool?